So this tutorial is about vector fields, and when we're talking about vector fields we are looking at a vector, just to remind you, is something that has magnitude and direction, as opposed to a scalar such as perhaps temperature, which just has a magnitude but has no direction. As it says on the slide here, vector spaces are normally 2 or 3 dimensional, and we describe them in a way such that the vector v, so here's the vector v, is made up of 3 individual vectors in the 3 planes. So vector I is in the plane O to x, or in the x-plane, and it has a magnitude of a. The second part of the vector is in the y-plane, and that is described as j, and that is in the O to b along the y-plane, and it has a magnitude of b. And the third part of this is in the z-plane, and that is when we have 3-dimensional vectors, and that is in this plane here, the z-plane, so from 0 to z, with a magnitude of c. And when we add those 3 unit vectors with their individual magnitudes of a, b and c, the resultant is vector v. And the magnitude of vector v, as it's shown here, is a squared plus b squared plus c squared, all square rooted. So let's have a look at a couple of vectors. We'll define a couple of vectors here and do a couple of sums. So vector 1 is 2i plus 3j plus 4k, and vector 2 is 3i plus 4j plus 3k. Good. So as I mentioned over here, the magnitude of any vector is the square root of the sum of the squares of each of the unit vectors that make that up. So let's have a look at v1. So we'll say that the magnitude of v1 is equal to, and I always get these square roots, they're always wobbly, 2 squared plus 3 squared plus 4 squared. And if you do that sum, and feel free to pause and do that sum for yourself, you'll find that vector 1 magnitude is 5.39 of some unit. So why don't we go ahead now, pause the video and have a go at vector 2, the magnitude of vector 2. So just to go through that now, vector 2, we have the square root of 3 squared plus 4 squared plus 3 squared. And if I've done my sums right, I think that is 5.83. Good. So what else can we do with vectors? What else would we want to do? So presumably, now that we've got 2 vectors, we would want to find what the resultant of those vectors are. And got a natty picture here, sort of a real life situation where the work done is the product of a couple of vectors. So you've got a vector here, a force here, and a force vector here, which gives you a resultant vector, which is the product of those two individual vectors. So the product, or as it's sometimes known as the scalar or dot product, is written in this way, and it is equal to the magnitude of vector 1 multiplied by the magnitude of vector 2, and you can see in our example we've already done those magnitudes, cos theta. Now also the magnitude of the dot product is given down here by A1 times A2 plus B1 times B2 plus C1 times C2. So why don't we go ahead and do this sum here over on our blackboard. So we're looking for, let's pick a different colour, we're looking for B1 dot product V2 in our own example. And remember from the slide that is going to be A1, that's a 1, A2 plus B1, B2 plus C1, C2. I'm going to write this out in longhand so that you can see what I'm doing. So I've got 2 times 3, and if we go up here, there's the 2, there's the 3, there's A, B, C, A2, B2, C2. So that's going to be plus 3 times 4 plus 4 times 3. And when you add them all together, the answer is 30. So now I think we've reached a point where we can now do this sum here to find out what the angle is between those two vectors, vector 1 and vector 2. So if you're asked for the magnitude, we've done that. If you're asked for the scalar product or dot product, we've done that. And now if we're asked to find the angle between the two, that is given by, as it says here, if you do a little bit of, so if we take this sum, or rather if we take this sum here and we transpose that for cos theta, we find that cos theta after that transposition equals the dot product V1 dot V2 divided by the scalar product, so of V1 V2. And that, well, we know what the dot product is 30 divided by 5.39 times 5.83. Let's write that down. 5.39 times 5.83. And that equals, we'll put it over here, 0.95. So if we say that cos to the minus 1 of 0.95 equals 17.29 degrees. So here we have the magnitude of V1, the magnitude of V2, the scalar product of V1 dot V2 and the angle between 1 and 2. And that completes this short tutorial.